Hi, I'm Sadie Witkowski.
And I'm Ian Martin.
And you're listening to Carry the Two, a podcast from the Institute for Mathematical and Statistical Innovation,
aka IMSI. This is usually the podcast where Sadie and I talk about how math and statistics impact the world around us.
Usually because today we're doing something a little bit different and unique.
Hey!
While we're in between our more in-depth seasons, we wanted to bring something a little different. So for this 6-episode run between our main seasons, we have a special guest joining us.
Would you like to introduce yourself?
Sure. I'm Tiffany Christian. I'm a rising fourth-year PhD student at Northwestern University in the statistics department, and I used to know how to unicycle.
That's something you can forget?
I haven't tried since I learned, so maybe you could forget how to unicycle.
Do you just have really good balance? I don't even know how you get up there.
I bet you had a six-pack from using your core muscles.
Yeah, I was ripped when I was 13.
Okay, but to get back on topic, Tiffany is joining us as our Statistician-in-Residence to help us tackle statistics in the world of environmental and climate science.
Yay! I love giving my environmental nightmare statistical backing.
All right, let's get this show on the road.
I know you guys said that we would be focused on climate change, but I think today's topic is a parallel issue that's certainly affected by climate change.
That's right. Today we're covering invasive species, which, as a reminder to all our listeners out there, is when a plant or an animal or other creature leaves its original habitat.
Kind of like how gardeners define weeds as just something they don't want growing in their garden.
Yeah, so the USDA, that's the U.S. Department of Agriculture, defines them as non-native creatures that come into an ecosystem, and that their introduction causes or is likely to cause either economic or environmental harm. So invasive species can be introduced into an area by anything from ship's ballast water to logging for firewood, any of these kinds of things that bring along insects, or even accidental release, sometimes by people.
Oh, I actually have a very good example of that. And by good, I do mean horrifying. So I was listening to this Bill Bryson book about Australia called In a Sunburned Country. And he mentioned that there was a British dude called Thomas Austin, who in 1859 really wanted to hunt rabbits for sport while in Australia. So he had 13 rabbits sent to him because, God forbid you find a native animal to hunt or, pick a different pastime. Anyway, it only took 50 years for the rabbits to take over the whole country. It had devastating effects on the vegetation because they overgrazed and exposed the topsoil, which then blew away. And then this was followed, unfortunately, by a series of droughts. And so now there are many places in the country where you can't plant vegetation because all the nutrients have gone from the soil.
These are definitely the kinds of horror stories that ecologists are trying to avoid.
But at least with the rabbits, they're an easy invasive species to spot. I mean, even if they aren't easy to remove. But some invasive species are much smaller and harder to notice, and it can be really difficult to know which areas are particularly faced with a threat and that need extra protection. And so that's what we're going to be talking about today, using this really cool study that uses a spatial analysis to try to recognize and protect specific areas of a forest.
That's right. Today I want to talk about this 2014 study by Liang and colleagues that's called Spatial Analysis Facilitates Invasive Species Risk Assessment.
Okay, so what's the creature we're talking about here?
In this case, the authors are trying to look at different regions and regional hotspots for what is called the hemlock woolly adelgid. It's an invasive insect that's threatening native forests and particularly preys on hemlock and spruce trees. It was introduced as an invasive species, and now it's starting to take over these forests. So the study Tiffany mentioned is trying to see the areas that are at most risk, where we should be spending our money and our time for preventative measures to be the most cost effective. Basically, the study is trying to look at the ways to figure out probability of invasion based on, for example, known locations of where the bug has been seen in the past or other environmental factors. And to find a way to reduce the uncertainty in this modeling so that they can really be like, yes, these are the top 5 hotspots where we need to intervene. And these 5 areas we should keep an eye on, but are probably going to be okay.
I get the reasoning behind the study, but I know nothing about spatial statistics. Tiffany, can you fill me in?
Yeah. So spatial statistics is an area of statistics where the location of the data is just as important as the data itself. So whatever variable we're looking at, it's important that we found this particular thing happening at that particular location. And in this paper, location provides a lot of information. You can imagine that if you picked a random point in the forest, there are many different environmental variables you could look at. You could look at elevation, temperature, soil conditions, sun exposure, how windy it is, and the list goes on. Since they wanted to investigate areas that were vulnerable to hemlock woolly adelgid, they looked at stands of hemlock and spruce in the mountains of Kentucky. They wanted to model the areas that would be hard to monitor consistently, so they picked high elevation and mountainous areas that would be difficult to access. They wanted to have a way to know, okay, we have vulnerable populations, how often do we need to send people out to monitor, and what factors are going to influence their vulnerability? One of the most important things about the location was that the trees that the insect attacks are there. So that's one spatial variable.
Okay, yep. Must have trees that are under threat. Check.
They also wanted to know, how could the insect even get to this particular area? So they looked at old railroad routes and active recreational trails like hiking trails, which can create corridors through these natural spaces.
Ye old-timey hitchhikers catching a ride, because insects are famously avid hikers and love taking the train.
So do the hemlock woolly adelgids get their own Amtrak stop?
Boo.
Yeah, they literally hitch a ride. So they had the railroad routes, the incline of the terrain, the temperature, different climatic variables, and wind. Because the hemlock woolly adelgid is so small, it can be blown around by the wind. They had all these variables, and they basically combined that information with data of where the adelgid had already been spotted, and data that showed the areas where the adelgid might want to live.
And these are all spatial variables because they differ across the map, yes?
Right. Although some of this data is a bit incomplete. Like, they know where the adelgid has been found so far, but they're not testing everywhere necessarily.
Yeah, they had presence data of like, okay, we spotted it here and here, but they didn't have absence data because it's a small bug to check for. So just because we didn't see it in a place doesn't mean that it's not there. And so they used a particular kind of statistical model where that data, presence-only data, is okay to use. And that's what they put that and all the other variables into a model.
And just so our listeners know, we don't mean a physical model like a miniature forest. Rather, in this case, we're talking about a computer program containing lots of mathematical equations that help us make predictions about the system's behavior. Think of something like a weather prediction model.
So what did the model spit out?
Basically, the model tells us which area is susceptible. So you could look at a map and the model would be like, this mountainous area is highly susceptible, but this other area is not very susceptible. So they had several different models, and each model would spit out a different amount of areas that are highly susceptible. So they can compare models, and one that has a lot of highly susceptible areas and one that has a little highly susceptible areas. And if they looked at one that had a lot of highly susceptible areas, that could be like, okay, we have to protect everything that this model says.
But it could really not be feasible to do that.
Right. But it also could mean that we need more resources from the state to try to get more hands or feet on the ground for that. Or we could look at the model that had less highly susceptible areas and really concentrate our resources on those smaller areas that were protected by the model. So they could use this model comparison to determine where the intervention was needed most. And they also did a thing where, based on the results of the several different models they fit, they were able to look at the areas that were considered highly susceptible and see, like, is there a hotspot? And a hotspot is just a way of saying, like, are all your neighbors sharing a similar value? So if you look around you and all your neighbors are highly susceptible, you might be in a highly susceptible hotspot.
Yeah, so say if I'm in a theater and I hear several people around me who are coughing, I might be in a highly susceptible hotspot for getting sick.
Yeah, you might have that COVID cough, someone right next to you, and that means you're in a hot spot.
Also, just listening to you list all these variables is just another reminder of how complicated everything is surrounding environments and ecosystems, and just how delicate it all is, like how one action can have so many consequences that we can't even comprehend or even think about.
I'm still caught by the complexity of this data. For the adelgid, you have a present signal, not an absent signal. But then you have variation of elevation, which is giving you multiple degrees that you can be looking at. And then you have railroad presence or absence, which is a binary. It makes me think of all those like transparencies that you could layer over a map on top of each other. But some are binary and some aren't. And how complicated putting all that together is in a model. All that work just to come up with a value where you can look at some policymaker and say, I did the math and we need to worry about block 3B. Like, that's crazy.
Yeah, the transparency is a really good analogy because that's like in the software that these kinds of researchers use. The software is called GIS, and it's literally layers. You can stack layers of data on top of each other, and you can pick from the layers that are going into your model. So you can remove things and add things based on the whole surface of data that you have. And that's really how I like to think about spatial statistics. These things are happening on a surface, because they're happening on the surface of this case, the Earth. So at each point, there are many different variables we can measure at any given time, and everything really is connected.
And some are connected by railroads. But actually, you mentioned that the authors of the paper seemed surprised by how important the railroads were.
The researchers were surprised how little wind was important in their model, given that in other papers, it's a known dispersal pathway for the adelgid. They think that for their particular areas of interest, the patches of adelgid habitat are more dispersed. So the wind could blow adelgids into an area where they don't have a good chance of surviving, that don't have as many trees that they can live on. So because the habitat is kind of patchy, the wind isn't really a good dispersal mechanism. And the corridors, like the railroads and the hiking trails, act more like highways where the bugs can move from patch to patch where their habitat is suitable on birds, deer, humans, and other wildlife.
Wow, I'm just sort of reveling in the complexity of it all.
Yeah, it's just really cool to think about like trying to make these really targeted preventative measures based off of having a really good understanding of all these diverse variables in an ecosystem. I just think that's so cool. And a good way to think about improving conservation, like getting your best bang for your buck on that conservation.
Statistics to the rescue!
If you're enjoying this show and learning about the important research, here's another University of Chicago Podcast Network show that you should check out. It's called 9 Questions with Eric Oliver. Have you ever wondered who you are but don't know who to ask? Then join Professor Eric Oliver as he poses the 9 most essential questions for knowing yourself to some of humanity's wisest and most interesting people. As always, don't forget to check out our show notes in the podcast description for more about this research on invasive species.
And if you like the podcast, subscribe to the show and give us a review on Apple Podcast or Spotify or wherever you listen.
By rating and reviewing the show, you really help spread the word about Carry the Two so that other listeners can discover the show.
And for more on math research being shared at IMSI, be sure to check us out online at our homepage, imsi.institute. We're also on Twitter at IMSI_institute, as well as Instagram at IMSI.institute.
How do you spell that again?
That's IMSI, spelled IMSI.
And what are your mathy questions? Maybe you have an idea for a story on how mathematics and statistics connect with the world around us.
Send us an email with your idea.
You can send your feedback, ideas, and more to sadiewit@imsi.institute. That's SADIEWIT at imsi.institute.
We'd also like to thank our audio engineer, Tyler Dammy, for his production on the show.
And music is from Blue Dot Sessions.
Lastly, Carry the Two is made possible by the Institute for Mathematical and Statistical Innovation, located on the gorgeous campus of the University of Chicago. We're supported by the National Science Foundation and the University of Chicago. Until next time.
See ya.
Adelgid. Dope. I mean, that makes sense. Adele, British, sure.
Adelgid. This insect also likes writing sad piano ballads.
Oh my god. This this name of the bug is throwing me off.
Two things. One, adelgid. I just picture a bug sitting at a piano playing like do 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 do. Someone like you. And this is where we have the ad break for Amtrak, I want to say.